So hi guys, my name is Nathan. You can ignore the name on Zoom. I'm at my boyfriend's house, and this is his account that I'm signed into. But my name's Nathan. My Discord is at Bakuda. That's my Twitter handle. A little bit about me. So I studied computer science at CU. I'm a bit of a C++ fanatic, so I am a programmer. I also enjoy other languages such as Rust and F#. Specifically for programming, I'm into game engine programming. Anything that specifically relates to systems design or game engine architecture are my two areas that I'm most specifically interested in. And then in terms of like any kind of work experience I've done, I interned at Blizzard, not this previous summer, but last summer as on their game engine team. And then this past summer, I interned at Tesla, where I worked as a video game engineer. All right, so let's begin. So let's have this theoretical scenario, right? So here we are, or in this case, this could be me, or this could be any sort of developer. We're gonna work at a company, maybe not Blizzard, let's call it Lizard. All right, so we work at Lizard, and our boss comes up to us one day and is like, hey, I have this amazing idea, right? And he's like, here's my idea. I want to make asteroids. And you're like, okay. So here we are, we're a smart developer, we made games before, we know how to do this. So we're gonna take a simple game scene here and we're gonna kind of break down its parts. So we have these things that are flying around. These are the asteroids in the game. We have this triangle thing in the middle that the player controls. This is good. This is kind of like the spaceship. We have these bullets that the spaceship can fire at the asteroids and destroy them and break them into smaller pieces. And the last part of our game is we have a UI kind of in this corner, which keeps track of our lives and the total score. There's a few things that I left out of normal asteroids, but this is mostly just for simplicity. All right, so we've made games before, right? So we're kind of going to go down our traditional approach, right? We can kind of think of this, I don't know if anyone's used like Unity or Unreal or anything like this. We generally have some sort of like base class of all of our of really anything in our game, and just for purposes, we're going to call this a game object. So we have this game object class, and we're going to have some renderable class, which is going to derive from this game object because in our scenario, everything in our game can be drawn on screen, right? We have our spaceship, our asteroids, our bullets, and our UI. These are all drawn, so we're going to derive a renderable from this game object class. UI, we're going to derive that from our renderable because the UI, of course, can be drawn, but it doesn't really have much like functionality otherwise than just being drawn and kind of like updating every frame or so. Next part we're going to do, because UI doesn't necessarily have physics, we're going to create this kind of has physics class. And then we have our three other big components of our game. We have our spaceship, bullet, and asteroid. These are all, of course, these are going to have physics. Specifically the spaceship, it's controllable because the player can interact with the spaceship. And finally, our spaceship, our bullet, and our asteroid, they're all collidable, right? The spaceship can bump into an asteroid, a bullet can bump into an asteroid, and so on and so forth. So these are all going to inherit from collidable, which then inherits from has physics, right? And this is a pretty good general, I'd say pretty good hierarchy for a simple asteroids game. In code, as a heads up, there will be code in this talk. I do my best to walk through it. It's not too much and it's not too difficult to understand, but it would maybe look something like this. So we have this class here, which is our game object class, and game object will have some virtual function called update that takes the delta time, which is the time since the last frame, for example, and it will have some update function. And of course, our has physics, our UI, and all our base classes derive, and they can implement this update function because everything has slightly different functionality. And then in our main game loop, we'll create a vector of these game object pointers. We'll call this our world. We'll add, in this case, we're adding an asteroid, then we can add our spaceship and whatnot. And then in our main for loop down here, we're just going to get the time since the last frame, and then we're just going to iterate through every object in our world and call update. This is pretty standard, I would say, game design game loop. So all is good, right? We have a working asteroids game. Boss is happy. This is awesome. Uh-oh, we get an email from our boss. What does it say? Well, they say, dear, enter your name here, great job in the game. However, our consumers are saying that the game is a little too easy. Many of them have requested the addition of invisible asteroids. Can you do this? Thanks, your boss. You're like, all right, this is no big problem, right? So here we are. We kind of look here at our game, our hierarchy tree. We're like, all right, we kind of have this asteroids class, right? What is an invisible asteroid? Well, maybe it's just like something that can derive from this asteroid class because it overall has the same functionality of this asteroid maybe, but it just has a property or two changed. However, I think as most of us can probably see here, there's a big problem, and this is the fact that an invisible asteroid is not renderable, right? It's invisible, so we're not going to draw it to the screen every frame. But with our current hierarchy that we have here, invisible asteroid inherits from asteroid, which in itself inherits from renderable. And this is not something that we necessarily want. So let's assume that we're somehow able to combat this problem. Maybe we're able to shift some classes around. We're able to introduce some interfaces between classes. We can have an asteroid and an invisible asteroid that are both collidable, but not necessarily both renderable. So cool. Maybe we theoretically solve that problem. Email number 2. Awesome job adding the invisible asteroids. However, now our players are saying the game's a little too simple. Perhaps we can add some different bullet types. You can do exploding bullets, piercing bullets, that like pierce through an asteroid and hit the one behind it. That's kind of cool. Or maybe, a bullet that does both. It'll explode and it'll pierce through, add some fun game functionality. All right, again, we take our game, we take our hierarchy tree that we have this bullet class. And again, we'll kind of do it like an asteroid, right? We can have an exploding bullet, we can have a piercing bullet. But he wants it exploding, our boss, they want a exploding piercing bullet as well. So how do we do this? This is where it gets a little difficult. So here we have what's called diamond inheritance. It's basically where you have some class that has to inherit 2 different classes because it wants both of their functionalities. However, this is not actually possible. There's a lot of, like C++, for example, which is my primary language, you can do multiple inheritance, but I know other languages don't actually allow you to do this. And this is also not good because this exploding piercing bullet is kind of getting 2 copies of this bullet data inside itself, right? So a bullet might have a position, for example. Exploding bullet also has a position. Piercing bullet has a position. But in this multiple inheritance case, it would have 2 positions, which again, this is a problem that we can run into. So what is our problem here? Well, our problem, I would argue, is kind of our initial strict object-oriented programming approach to this game. And I won't say this is really anybody's fault. I feel like a lot of programmers, when we're introduced to programming, object-oriented is kind of how we're taught to view things. It's a very easy way to view stuff. We kind of view like game objects, for example, as we would view them in the real world. However, as we saw some problems here, when you get these deep inheritance hierarchies, these are very inflexible. They're hard to change, as we saw kind of with our invisible asteroid, right? We wanted to add a simple base class, but we were kind of already glued into this whole hierarchy that we had created initially. Also, most game objects and behaviors, as we saw, don't really fit nicely into these hierarchies. Again, as we saw with like the diamond inheritance problem with the bullet. So maybe this is not actually the best approach that we can have to our asteroids game. Right, so why did we even choose OOP in the first place? Other than it being comfortable, why is OOP popular? I'd say one of the primary things that OOP gives us is the ability to reduce code duplication, right? So as we saw, we have these renderable, has physics, collidable, and controllable. All these are kind of like, these are classes that add more so like behavior and functionality to things that derive from them, right? So because our bullet, our spaceship, and our asteroid, all these things can collide with one another, and we don't have to necessarily like duplicate this code every single time we want a new class that is collidable. We want to have some sort of like generic interface that our game objects can derive from, so that they just automatically implement this collidable. But what if we do something like this? So what if we kind of scrap this whole hierarchy tree thing, and we kind of just set these to the side, right? So we instead just have like a render, which might just be like, in our case, it might just be like a mesh or like a color. So we kind of want to take it out from this whole class idea and just kind of put it as some data, right? So in this case, we have our render, our physics, our collider, and our controllable, but they're not necessarily like related in any way. This is what I'm going to call a component. And then, for example, we have our asteroid here, right? As we saw in our asteroid, again, our asteroid was something that derived from all these classes that we had from this class hierarchy that we had. But for our purposes, I'm going to call an asteroid an entity. And what is an asteroid, as we saw before, right? It was something that derived from, from the game object, and then from renderable, from has physics and collider. But what if we just place all of these things sort of in sense into this asteroid entity? And again, we can kind of replicate this with all of our other game objects that we have here. So here what we have is instead of having this inheritance hierarchy, each of our individual game classes are just kind of composed of these what we call components down here. So how does this fix our problems that we have before? Well, for our asteroid example, right, we have our asteroid, which in our case has render, collide, and physics. What's an invisible asteroid? Well, it's nothing other than an asteroid minus the render. And as we see here, there's no need to kind of change inheritance hierarchies or anything. All we simply do is we simply just grab out that render component. Again, with our bullet example, right, we have our base bullet here. We have our bullets, which, you know, we might have an explode, we might have a pierce, you know, component we can call them. And then how do we do the exploding piercing bullet? Well, easy. We just make another bullet type and we just include the pierce and the explode, right? Again, there's no like sort of dependencies between all these instances of a bullet. All right, so we're going to kind of dive into actually what ECS is, right? The title of my talk. Some of you might be wondering, you know, what is ECS? You still haven't actually described it yet, but I want to take a brief step aside here. So this book here, Game Programming C++, this is one of the first programming books I ever got when I started doing game programming. And and this book, it kind of introduced the idea of components and kind of an ECS component design, but I would argue this is not the approach that we're going to be taking. So in general, this is kind of how this book laid it out. We'd have kind of this component class, right, that again would have this update function and it would have some like pointer to whatever entity owned it, right? So in our case, we could think of a component as like, you know, we'd have like a render component, which would derive from this component class, you know, override this update function, and then it would have some pointer to whatever entity owned it. And then entity we would view as like, you know, an array of these components, and would have some add component and would just have an update function that would internally just iterate through all of its own components and add update. However, this is what you would call an entity component systems. And this is not what we're talking about today. The main reasons we're not going to do this is that we have this problem where behavior is coupled with data, and I will explain why this is a problem later. But right, so we have this component which may contain some data, and then the behavior which is in this update function, and we want to find a way to separate these. And also in this case, it's super difficult to deal with intercomponent dependencies, right? If your render component for some reason relies on your like collider component, like setting up these dependencies is really, really difficult. And this is what we're finally going to talk into. So what does ECS actually stand for? So ECS stands for Entity Component System. And it's important to understand that these are actually three separate words. So we have entity, which is a word by itself, component, and system. So I'm going to take our asteroids example. Components we can view as I kind of described before, components are nothing other than structs of data. So again, so for a physics component, for example, this might contain a position and a velocity. Or a collider component, it might contain some axis line bounding box, and maybe like this, or like maybe like if it was a circle, it contained like the radius for the circle's collider component, for example. An entity is nothing other than a composition of these components, as we saw before. And now what is the system? Well, a system is the behavior that actually operates on these set of components. So as I said before, we want to find a way to sort of separate data and logic, right? We don't want to have our render component in charge of rendering itself. The render component is only there for holding the information that's required to render. So in our case, we're going to have a physics system, and all the physics system cares about is it cares about these physics components. It's going to take these physics components and then, you know, perform the calculations to simulate a physics step. In code, what is this going to look like? Here's a very simple implementation. We'll have a base class, which is our component. This is more so just for tag types. You'll see that there's actually no virtual functions here, so this doesn't actually introduce any overhead when it comes to using virtual functions. You'll see your physics component, which is going to derive from this component. And note here, so it's important. So before, the problem with inheritance that we ran is that inheritance ran deep. So when we saw our initial tree, right, like the tree it was super high up here and it was like 4 or 5 levels all the way down here. The idea with components is that this is a very wide, wide inheritance hierarchy. So, right, so each component is only going to derive per se once from this initial just component struct, more so just to act as a tag more than anything. Our entity class is going to be again, a vector or an array of these pointer to these components. It'll just have a simple way to add a component, a simple way to get a component that might exist. Of course, we're going to turn like an optional because, again, an entity may or may not have the component. Our world is just going to be a simple vector of these entities, and our game loop, so I guess we don't really have per se game loop this time, but how would we describe our physics system, right? Our physics system is going to take a reference to whatever this world is. It's going to iterate through every entity, and if an entity has this physics component, it's going to do some calculations.
I think the better way to describe it is the update function of the physics system.
Yeah, exactly. Yeah. So Leslie points out a good, yeah. So like you can kind of view the update step, but more so that's kind of put into where the system's behavior is. So the systems, each of the systems kind of act as like a part of the update step. So in our case, you would have multiple systems and each of these you would fit inside that game loop. So what are the benefits of ECS? We get composability, which is really nice. It's easy to make entities by just composing components or throwing out some components. It's super modular. It's super easy to refactor, right? As again, back to our asteroid example, it was super easy to introduce a invisible asteroid. We didn't have to, change this whole hierarchy. There's also fewer component dependencies because these component dependencies can actually rely inside of our systems that we have. And also, again, there's a separation of this data and logic, which is super nice for our case. So all is good, right? Game was a success. We're able to add more features super easily. We can, again, we can add more entities. We can destroy entities, and it's very simple. Thanks entity component system. Uh-oh, here we go again. We got another letter from our boss. What does it say? It says the game has been a success, especially now as we added, more features. However, now the customers are complaining about lag, low FPS, slow loading times. Can you look into this? So here we are, we're the developer. We're pretty smart, right? So what are we gonna do? Our problem is in this case, low frames per second, there's lag. So we're gonna do some performance measuring. In this theoretical sense, we do some performance measuring on our game and we find that the problem is here. It's in this physics system loop, but specifically in this line right here. What are we doing here? Well, our physics system only wants these physics components, but every time it iterates through an entity, it has to ask this entity to see if it has a physics component, and then if it does, then it can perform the calculations, and if not, obviously it has to ignore it. So I want to take a look at how these. So how does what we have, how does it actually look in memory, right? Because when you're doing any sort of performance testing, or when you kind of want to understand why ECS is really good, you kind of have to go a little lower level and you kind of need to look at hardware. So how is this going to look at memory? Well, so again, here we have kind of what we had before. We have our entities and our components. It's going to look, and here's our world example, and our world is going to look something like this. Right, so here we have our spaceship entity, our bullet entity, our asteroid entity, and our UI entity. And they're stored in this array. And this is what we would call an array of structs. So this is where data for different fields are interleaved, right? So as we saw, back to our physics system, the physics system wanted just this physics component, all these physics components, but these are separated, right? They're interleaved by the other components that the entities might contain, have it be the render or the collider. Another important thing to realize is that here we have a unique pointer. So this is C++ specific, but you can kind of think of this as just a pointer in general, or a heap allocated object. So we need a pointer to this component. And why is this? Well, we have to allocate it on the heap, mostly because we don't actually know the size of the components at compile time. This is a sort of runtime polymorphic thing. So, and you can't have arrays of different types, right? So you can't just have an array and then add any types to it without some sort of overhead of like, some sort of type erasure or something like that. So back to here, here's our structure of our array of structs. And this is, again, because of this pointer, this is actually what this looks like. So each of these components that we had, they're actually not inside the entity per se in that location in memory. They're actually a pointer to somewhere on the heap where the component data actually lives. So for our asteroid example, right, as we said, this rendered component doesn't actually live wherever this entity lives per se. It's some pointer to somewhere on the heap where we allocated this memory for this render component. And why is this bad? Well, why could this possibly be making our game slow? As I said, the components inside the entities are merely pointers to data on the heap, and this requires what's called pointer chasing and memory indirection, which I'll explain why it's slow a little later. Another thing we need to ask is, where are these components used, right? Well, they're used inside of systems. So something we can think to ourselves as well, like, what does the system want? Well, the system it only wants the components that it cares about, right? The physics system doesn't care about what an entity is. It doesn't really care that there is such thing as an entity, or that an entity might have a render component, or that an entity might have a controllable component. All it cares about is these physics components which we can put into our entities. So is there any way for us to optimize sort of this component memory access, right? Is there any way for this physics system to very quickly get these components? So I'm going to take a slight digression, and we're going to dive a little bit into hardware and kind of what how CPUs and this idea of data locality works. So here we have our CPU. CPUs stands for the central processing unit. It's essentially it's this little place inside, you buy a CPU, but it's basically the place inside your computer hardware where the main instructions are run, right? It's where adds, multiplies, divides, subtracts, or it's basically where it's the primary powerhouse of your computer, is how you can think of it. There are these things called caches. Caches are small bits of memory that are located close to the CPU, right? So we have this L1, L2, and L3 cache. As the cache number increases, the size of the cache size increases, but also the physical distance away from the CPU increases as well. So L1 cache, for example, I think I actually have this written out here. I'll get back to that in a second. And then we have this thing called RAM. RAM is our main memory. I think if you've ever built a PC before, right, you've had to buy RAM. This is kind of what the idea of it is. So this is also called main memory. Just on my machine, I performed just a grep of the sizes for my machine. As you saw, the L1 cache, it's 256 kilobytes. L2 is 2 megabytes. L3 is 16 megabytes, and I have 32 gigs of RAM. Again, you don't actually have like 32 gigs available to you, but so as you see, right, they each get larger and larger, again, up to RAM, which has 32 gigs. So how does data loading actually work? So the CPU, right, he's going to say, I want the data that's at memory address some hexadecimal number. First thing it's going to do is it's going to go to the L1 cache because it's the closest. And it's going to ask, hey, do you have this data that I want? The cache is going to say no, and this is what we call a cache miss. CPU is going to go to L2 cache, not find it there. L3 cache, not find it there. And finally, it has to go to RAM. RAM is where it will actually live. Again, there's some like stuff I'm kind of skimping over here, but this is the general idea. So it'll find the data in RAM. And this is our data that we got. However, so the people who made CPUs, they're very, very smart individuals. And they found out you have this notion of something called a cache line. A cache line, as I said here, is the unit of data transfer between cache and main memory, which on most modern like computers today, if you run like x86 architecture or even like modern ARM and stuff, it'll be roughly 64 bytes. So they found that loading 64 bytes of memory from RAM to the CPU takes just as much time and is just as efficient as loading 1 byte. So if you're gonna load memory from RAM, you may as well load as much as you possibly can. So our CPU, right, so it wants this memory. So it's going to take this cache line and it's going to store copies of it in L3, L2, and L1 cache. Yay, so that's good, right? So next time the CPU comes around, it's like, hey, I want the memory at address, whatever. It'll look in L1 cache, and because we've already accessed it, this is called a cache hit. And they have these two ideas called temporal locality and spatial locality. So temporal locality is just kind of the idea that in terms of time, whenever you access something, you're likely to access it again within a short period of time. And spatial locality says that whenever you access some data, you're likely to access the data that's close by to it. So why did I tell you all this, right? Why does this matter? Well, this is a very, very crucial diagram that's important to understand. So this is from Jason Gregory. He is one of the principals. I don't know if he works at Naughty Dog anymore, but he was one of the principal software engineers at Naughty Dog. He was big on performance. And he actually wrote a few awesome books. If you're ever interested in game engine design, he wrote some books. I believe they're called Game Engine Architecture or Game Engineering, something like that. But you can just look him up. But anyway, so he was big on performance, and he measured the performance as how long does it take to load memory from these caches or from RAM to the CPU. If we look at L1 cache here, it takes roughly 3 CPU cycles, right? This is basically no time at all. L2 cache takes 20 plus cycles. We don't have L3 cache here because we're looking at, I think, at PS3, PS4 architecture, and they didn't actually have L3 cache. And then RAM here, right? takes 200 plus cycles. This is insane. Compared to this, L1 cache, this is almost like 100 times slower, which is absolutely insane. So right, we could load 100 of these in the time that it takes to load one of these. Again, I'm saying 200 plus, or maybe looking at like 300 cycles. But the idea is that it takes a really long time to load memory from RAM into CPU as it does to load memory from cache into CPU. So back to asteroids finally. Sorry for that little digression we had there. Right, so here we have here's our current layout that we have of our game, right? We have all these entities and their components. Remember, these are actually not the components, these are pointers to the components which live somewhere else on the heap. So let's take these physics components, right? Is there any way we can group these together? Easy, right? Just pack them into an array. Simple as take all these physics components, take them out of their entities and just throw them together in their own array. And we can do this with all of our other components. So right now, all these components are in their own individual arrays. And we can this time, so an entity is still theoretically kind of a composition of these components, but in actuality, an entity we can kind of view as an index into this components array. So we have our asteroid here again. We can view it as index 0. And it's going to be the 0th with index of all these. So it's going to have the render component, colliding component, physics component, and because it doesn't have a control component, we're just going to throw null here for the meantime. And this is what we called a struct of arrays. This is a naive implementation. I'll get back to later. But the idea here is that instead of an array of structs, which we had last time, which is an array of these entity structures, we're going to have a struct instead of each individual piece of data that's important to us. And this whole idea kind of stems from the philosophy of data-oriented design, which is mostly about organizing your data for efficient processing. So now we're going to look at why, again, I kind of showed you how, why it's important that we try to keep data located in cache versus in RAM, right? Because we have that performance. But how does the struct of arrays versus the array of struct actually benefit us? So here we have our physics system. Here we have the heap memory for our array of structs, and the physics system, again, it wants these physics components, right? So it has to, so every time it iterates through an entity, it says, hey, entity, do you have this component? And if it does, it has to load that component into memory, or specifically into cache so we can access it. However, each time we access one of these physics components, as we saw from last time, it's going to load the entire cache line around the physics component into cache memory, right? But the problem is here, we don't really care about this data that's right here, right? Because this physics system only cares about physics components. So, maybe there lives some collider component over here or something like that. It's going to load this into memory, but the physics system does not care about this. So it's going to be loaded into memory and then it's wasted. However, in our heap the heap for our struct of arrays, which is kind of our new version of this, the physics system, it wants these physics components. But this time when it loads them into memory, because we have this packed array of these physics components, as it loads cache lines, these cache lines are going to be filled with these physics components. And this is awesome for us. So what happens is when the physics system first reads the data for this component, it'll ask for the next one. The next one's already going to be there in cache because it was loaded in that cache line. And this is a huge performance win. In code, the general idea is kind of like this. Again, this is the naive kind of implementation. We're going to have the struct of components, and we're going to have a vector of each of our individual components. And our physics system is just going to look like this. It's going to take our world or whatever. It's going to take and it's going to iterate through our just the physics component within our world, and just update those specific components, right? It doesn't need to check. I'll get back that. I'll get back to that in a sec. But it doesn't actually have to iterate through the entities. It just iterates through the components. So here's the main problem, right? We have these nulls here, right? And this isn't good for us, right? Because this is wasting memory with empty slots, right? Because nothing actually lives here. And also the system, again, like I kind of said before, as it's iterating through these components, it has to check, if it's not null, I can do it, else I can, perform the calculations with it. So a simple solution, right? Oh, and then also another problem that we have is that our systems, they may want entities with just more than one component, right? So we may have a collider system here But the collider system not only doesn't want the collider component, it may also want the physics component, because the physics component might contain some other information that it needs to use its calculations. And this is very, very common among systems, is that they don't normally just use one component. So the idea here is to remove all these nulls and just pack everything into a very densely packed array, right? So there's no more nulls here. And we just have these contiguous arrays with no gaps in them. However, we have this problem, right? Because asteroid before, it was just kind of an index into this, right? But the problem is this asteroid doesn't actually own this control component. So instead, we kind of need to view entities in a different light. Entities, this is just kind of a general definition of them, but you can kind of view them as like unique integrals. So each entity is going to have its own sort of integral identifier. So that could be like an integer, like an I32 or an I64. That the components arrays can use to identify the existence of a component for that given entity. So as I said before, there's no more null components and we're not wasting memory. So our asteroid, it might be some unsigned 32-bit integer. We can view it as a way to ask these component arrays, hey, give me the render component for this guy, right? And it'll sort of be references to all these components that may not necessarily live in the same index slot. And again, this is just a very kind of like high-level overview of how this would work. But this is really only one of the possible solutions that we can do for ECS. ECS is nice because it's kind of just an overall way to architect our games. And ECS kind of allows us to have the ability to move our data around, right? Because the systems, again, they only care about specific components, but they don't really care about where the components live or how they exist in memory. But before, with the entities, we had to keep them specifically grouped together. I'm going to jump through quickly here some popular ECS libraries. I'm going to take a dive into a few of them. So for C++, I have one for C, there's some C# ones, Rust and Python. You'll see here if there's an asterisk biome, that means it's more than just a library, it's actually a full game engine. So you'll see like entities, or not entities, Unity's dots framework. As we know, Unity's a full game engine. If we jump down to C++, probably the most popular one is called Entity. But Halley and Crown, these are all fully fledged game engines. But here are some popular libraries that you can use ECS upon. So I'm going to jump through a few kind of how these actually implement ECS under the hood, because before there's actually some limitations that you run into if we just have this idea of like a packed array and then an entity is kind of just a reference into these arrays. Like you can't actually code that. There needs to be a little more kind of indirection in here. The first one is called bit masking. This is something that Specs, which is one of the Rust libraries, and EntityX, which is one of the C++ libraries, use. It's kind of this idea where you have your components, and they're just you can identify them via various bits, and then an entity is just kind of a mask of these. So for entity, it contains a position and a velocity. You'll kind of AND these two together, and you'll get this kind of tag here. And then there's kind of two big popular ones. This is one of the two. This is called the archetype. This is used in Legion, which is one of Rust's super popular entity component systems. And this is actually what Unity. So if you use Unity and with their upcoming dots framework, if this is what you're going to use, this is kind of how Unity implements their ECS under the hood. So this is called an archetype. So the idea is here is that all of our entities, instead of kind of being references into the specific component arrays, we actually group entities based on their likeness of components, right? So we have entity 1 here, which has a render and a physics component. Entity 2 here, which has a collider and a physics component. And as you'll see, they both share these physics components, but they differ in their first components. What we'll do instead is we'll group all entities that have the same group of components together. So entities 1, 9, and 3, they all contain only the render and the physics component. And then 5, 2, and 8 all contain just the collider and just the physics component. And this is specifically really, really helpful if you have systems that are going to iterate through groups of components, right? So if you have a system that iterates through collider and physics, it will just be able to iterate through this entire archetype. It won't have to iterate through one of those densely packed component arrays and then check to see if an entity has the other component that it wants. This also has some drawbacks though, as you'll find that adding components and removing components from entities can be rather expensive, because if you add a component to say entity 5, it has to change archetypes. The other is grouped, and this is specifically via sparse sets. This is what Entity does. This is the ECS library that I'm most familiar with. Also, I believe Rust has a ECS library called Shipyard that has begun using this, and I believe Specs is another one that also, it uses bit masking and this kind of sparse set. But the idea is here is that you have these two arrays. You have a sparse array and a dense array. So we have some entity that's going to come in. Oh, and you'll have a sparse and a dense array per kind of component, per component type. So you have this entity, right? And its ID is 1. And it's going to come in and we're going to match the ID with the index into this sparse array, right? In this case, it's index 1. And then we are going to match it with the first open slot in this dense array, which in this case would be index 0 because there's nothing else in this dense array. So we're going to say what index it lives at, and then we're going to have a map back to, so these are kind of like references to one another. We can say the sparse, you know, its index 0 is into the dense, and the dense says 1, which is my index into the sparse array. And then what you do is you'll place this component here in this component array at index 0. Again, we can do the same thing, right? So we have these more entities that are going to come in, and they'll do kind of similar things. So they'll index into the sparse array at their specific ID, and then they'll find the next open slot in the dense array, and then that's where the component will live inside the component array. And this is, so the drawbacks and the benefits of this is that being able, so your components are tightly packed together. As we saw with the archetype, you could have entities who had the same component, right, the physics component, but they weren't grouped together. This version actually keeps every single component of the same type in a single array. This has its drawbacks in the case where when you're iterating through entities and you want entities with multiple different kinds of components, you'll find the component array that the smallest component array for the components that you want, that's the one you'll iterate through. But then every single time that so just say you want the physics component and the collider component, you'll get the physics component because it's in that dense array, but then you kind of have to check if the entity has a collider component, or you'll have to essentially find a way to find the index into that collider component. Here's the entity. We're going to take a brief look at how this will look in code. This is just taken right off their GitHub page. Oh yeah, they're used in Minecraft not the Java Minecraft, but Microsoft's new one, which like has all the ray tracing and stuff in it, which is really, really cool. But so they actually use entity in their implementation. In code, how's this going to look? You'll create these free functions that will create your entity types. So first you have to include the library. It'll take this thing called a registry, which is kind of just like the world container that I've been talking about before. This registry, it's where all the components are actually stored. And then you'll just ask the registry to create you some entity. This is just some integer. In this case, it's an unsigned 32-bit integer. You'll ask the registry to give this entity a physics render collider component, and then you'll return the entity. And then for a collision system, we would ask this registry for a view over all of our components, for all of our physics and collider components, and then we can just iterate through this. And there's no checking needed here. The library handles all the kind of checking for you underneath the hood. So what are the ECS, or what are the benefits of an entity component system? They're very modular and composable, as I talked about before. It's very easy to add and remove components from an entity. Performance is also great. We have this insane idea of memory access efficiency, right? We're able to very efficiently access our memory and access our components via contiguous memory. And this helps with cache locality and loading data from cache instead of needing to go out to RAM to load this data. One other quick thing that I haven't mentioned yet is multi-threading. So ECS also can get a big performance when using multi-threading. So what is multi-threading? So on modern hardware nowadays, I talked kind of about the CPU before, but if you actually look at your CPU that you have, it'll have multiple cores. And each of these cores are again, the powerhouses of your machine, but it has multiple of these. So it's able to do work at like simultaneous work, right? It's able to use all these cores to work on something that's kind of independent of one another. So you can have my machine, I have an 8-core machine. So I can do kind of theoretically up to 8 things at once. Like my computer doesn't have to just do 1 task at a time. It can do 8 tasks at a time. Also, there's this idea of hyper-threading where each core can actually kind of do 2 threads instead, which is super cool. But But you got to be careful because there's this idea of data races, which is what we want to avoid when we do multi-threading. However, the way that ECS can take major benefits from multi-threading is that systems, so by separating the data and the logic, which is a huge point that I kind of emphasize throughout this, systems provide us the ability to see access patterns, right? Because what a data race is it's when you have two threads and they're both trying to access the same data, but one of them is trying to write to the data, or at least one of them is trying to write to the data, right? Because if both of them are trying to get this data and one's trying to write, the guy that's trying to read from it, he might get it before the write, he might get it after the write, he might get it in the middle of the write, and there's no way of knowing how you're going to get, and this can cause some serious bugs in programs. So how do we parallelize this? Well, I'm going to take an example in code, and this is using the Rust crate called Legion, and this uses the archetype. Just if anyone is curious. So we're going to include the library, of course. So our three components that we're going to have here is we're going to have a position, a velocity, and a health. Position and velocity are just two 32-bit floats, floating point numbers, and health is just one 32-bit float. We have our systems. We have an update position system. It's going to take a mutable reference to the position and an immutable reference to the velocity and some delta time that's just the time since the last frame, and it's gonna just add and then it's just gonna increment the position based off the velocity times the change in time. This is just simple physics calculations. We're gonna have a render system here, which is just gonna iterate through these positions, and it needs an immutable reference, right? So it doesn't actually need to write to it, and it'll just draw, or we can assume it's just a dot or something. But decrement health system, which is just going to take all the healths and it's just going to constantly subtract 10. Cool, easy enough. Looking at our main function, Legion provides this this API that's called a scheduler, and a scheduler is what allows you to kind of group your systems together and like execute your systems, but using parallelism, and I'll explain that a little bit more in a second. Right, so we'll have a scheduler, and we'll add our update position system, our render system, and our decrement health system. We have this world, which is again kind of the thing that holds all of our components. We'll add the entities, we'll add the components, we'll set up all our resources. And then we are going to execute. So the scheduler has this thing called execute, where it's going to take our world and our resources, and it's going to essentially call all these functions. I'm going to take specifically a look at the scheduler. So with the scheduler, what does it care about? It cares about system dependencies, right? So as I kind of talked about before with this whole data race problem, it'll look at all the dependencies that systems have. So by just looking at the function signature of the update function, right, we see it needs a mutable reference to position, which in this case is write access, and an immutable reference to velocity, which is read access. Render needs read access to position, and decrement health needs write access to health. Now we have a dependency conflict here, right? Render needs a read to position, but update needs a write to position. So what does this mean? To avoid data races, these two systems cannot run at the same time. Otherwise, again, I said the problem is that we don't know if the read is going to happen before, after, or during the write. So in this case, the scheduler can come through and it can be like, hey, this means that I can run the update position or the health system at the exact same time. Because as we see, all this needs is health, and this needs position and velocity, and there's no dependencies between these. Or it could run the render and the health system together, because again, there's no dependencies between them. And theoretically, if our position system needed only write access to the position, we'd be able to run these at the same time, because you can have multiple threads reading the same data. That's not a problem. It's just as soon as one tries to change it. So this is how ECS, by just looking at kind of the systems and their function signatures, this is how with ECS, how we can very easily implement parallelism.
I'm jealous. That's some like serious reflection going on here.
Yeah. Yeah, Rust is I don't know if anyone has tried Rust before. If you're interested at all in systems programming, or just kind of, actually not even just system programming, because Rust provides a pretty high level abstraction as well. If you haven't looked at Rust before, I would recommend looking at it. It's a great language. Specifically, they try to capitalize on no errors, or like no like runtime errors, like no segmentation faults, no data corruption, which is a big problem you have with C and C++. But Rust tries to kind of be a safe systems language. I would recommend people taking a look at it if you're interested. And they have, like I said, they have amazing like game development libraries. So just a quick recap here, right? We have entity, component, system. These are three separate words. Entity is just a composition of these components. Components are just the data that we need. And system is the behavior that will operate on sets of components. What's nice about this is that we have modularity and composability, amazing performance due to parallelism and due to memory access efficiency. And I just want to take a little side note here. So I was kind of crapping on object-oriented programming in the beginning. I'm not saying that OO by itself is inherently bad. Just the problem is for game programming, it may not be the best approach. Here's my quick little resource page. Here's a few of these libraries. The person who wrote Entity, which is the ECS library that I've used a lot in C++, he has an amazing blog. How he kind of goes into depth about, again, more ECS and how he implements his library. Unity, if you've ever used Unity before and you haven't heard of dots before, I would highly recommend looking at it because this is kind of the future of programming in Unity. I know specifically for the Intro to VR class, I think you use an older version of Unity. Again, like dots isn't supported here, but if you plan on using it in the future, I would highly recommend looking at their dots framework. Data-oriented design or data-oriented design, if you're more interested in that, here's a few awesome YouTube videos that I personally love about this concept. And then if you just have any questions or just want to talk about programming or gaming in general, my DMs are always open. Feel free to ask me on Discord. It could be in a channel or whatever. So yeah,